Okay, finally we got everything okay now. Okay now. Okay, so yeah, today we are just going to do midterm review. There is nothing too exciting. We are just talking about a lot of things that we have taught so far in this semester in a bit more organized order. Okay, and so first is some things to remember is these polymer and Hedema matrices. Probably already feel it. Hopefully you already feel it. So far we use a lot of things. A lot of time we use those poly matrices in our quantum computation. Okay, so once again you need to remember what are those three poly matrices. So you have poly X, poly Y, and poly Z, and they are written in different ways. It's written as big X, big Y, big Z, or as the sigma X, sigma Y, sigma Z. Or sometimes you want to come from 1, 2, 3, you have sigma 1, sigma 2, sigma 3. And there are those three 2 by 2 matrix. And also it means they are 1 cubic gates. They are this is 0, 1, 1, 0, 0 minus I 0, and 1, 0, 0 minus 1. And you see X and Z more often than Y, mainly because the Y has this imaginary number, so a lot of time people like a real number. And the important property of polymatrices are they are all unitary operators, so you can think of them as quantum gates. And but they are also Hermitian operator, means that you can think as they are observable to be measured. You can measure those x, y, z observable. Okay. So those are polymatrices. And there is also Hedema matrix, and it's really like a polymatrix. It's also unitary and Hermitian, and it is 1 by square root 2, 1, 1, 1 minus 1. Okay. And more property about polymatrix. So first we like to know the eigenvector of the polymatrices. And so the eigenvector for the x vector and the z vector are the most important one. You really need to memorize who they are. So eigenvector for z is this 0 ket and 1 ket. And it's just the standard basis vectors, so 1, 0 and 0, 1. And the eigenvector for x, we call it the plus vector and the minus vector. And the plus vector is because it's 0 plus 1, so this in terms of this matrix notation is 1 by square root 2, 1, 1. And the minus vector is 0 minus 1, and in terms of matrix notation is 1 by square root 1 minus 1. Okay. And then there is also eigenvector for y. It will be this y plus and y minus. So y plus is 1 by square root 2, 1 and I, and y minus is 1 by square root 2, 1 and minus I. And the important thing about Hedema is that, Hedema will swap between x and z, and in two different sets. So first is that you apply Hedema on eigenvector of x or z, then it becomes eigenvector of z or x. So Hedema on this 0 become plus, Hedema on 1 become minus. And then if you do Hedema on plus, then go back to 0, Hedema on minus, go back to 1. And also if you sandwich Hedema, sandwich z or x with Hedema, it becomes x or z. So hzh, it becomes x, and h equals z. Also Hedema square equal to identity. So Hedema is just its own inverse. Okay. So it's a nice thing about Hedema matrix. Okay. And Hedema square to identity. Well, Hedema square to identity is just because this Hermitian and the unitary thing. You can also derive from here. Okay, and well, let me try to fix these connections. Okay, maybe if see why is the connection so unstable? Oh no. Oh, maybe if I connect this better, or no, but it's not that one. Okay, so far nothing bad happened yet. Okay, anyway, so yeah, the three most important 2 by 2 matrix, X, Y, Z, and Hedema. And okay, more property about polymatrix. First is that the three of them will always anti-commute, means that you multiply two of them, and it will be the negation of the third. So xy equal to minus yx, and I think also xy will equal to iz, etc. Okay. And as we said, it's a Hermitian and unitary, so eigenvalues will be 1 and minus 1, and you can see those from just here explicitly. So you have a 1 eigenvector here and a minus 1 eigenvector here. Okay. And then also we can define those generalized polys. So if we have we can define generalized poly with this n dot sigmas, and this sigma vector is a weird notation that we should have said, but so we say it better now. So we define this weird kind of a three-dimensional vector, which in each entry is actually a 2x2 matrix. Okay. And yeah, so this is a vector of 2x2 matrices. Or if you think about in more programming way, this is like an array of 2x2 matrices. Okay. And then we can have also a three-dimensional vector of so n hat is a three-dimensional vector with three real number, and sorry, not n hat. Here we have n vector, and as we think n vector is a unit vector that's a three-dimensional vector, and so it has three real number entry nx, ny, nz, and we try to define this real number vector inner product with 2x2 matrix vector, and it becomes a 2x2 matrix. So we have nx times sigma x plus ny times sigma y plus nz times sigma z. So these nx look like sigma x, but they are totally different. So nx is a number, and sigma x is a 2x2 matrix, just this 2x2 matrix we talked about before. So this equation is a linear combination between three 2x2 matrices. Okay. And in the end, you get also a 2x2 matrix. And so this n dot sigma notation means you get a 2x2 matrix. And we like to say that for any unit vector n, this matrix is also like a poly matrix, and it's like a poly matrix in the n direction. And so you think about in block sphere, any point correspond to a n hat, and this n dot sigma correspond to the poly matrix. Okay. And it's like a poly in many ways, and the first thing that it satisfies is that it also has eigenvalue 1 and minus 1. So for every n that's a unit vector, this matrix also has eigenvalue 1 and minus 1, means that it's a Hermitian and a unitary. Okay. And yeah, so from this you can have that it's square equal to identity, etc. And yeah, and it has eigenvalue, and you can find corresponding eigenvector. The eigenvectors will be the correspond to the points on the block sphere, and also you apply this unitary, it will be rotation of angle pi around this n vector axis. Okay, and I guess a bit digression on the notation. So here I write this n hat, and this n hat actually equal to n, and I write n hat out of habit, because usually when there's a unit vector, a lot of time people will use this hat notation. To me, it's a vector with the length 1, but it's also a vector, so you can also write a vector here. Okay. And yeah, so that's a quick thing about poly matrices, and I guess yeah, and let's go to talk about more one qubit gates. Okay, and so we have basic gates in our quantum circuit, and they are most important four are those four we talk about. So we have HENMA, X, and Y, and Z, and then there are also two gates that are used quite often. Is a phase gate equal to basically square root of Z gate, that is 1i, and T gate, the square root of S gate, is 1 and e to the I pi over 4. And it's also called pi over A gate, because it's e to the minus I pi over 4 and e to the I pi over 4. Okay. Up to global phase. Okay. yeah, so phase gate and T gate. And yeah, a bit more notation, we have delta function. This symbol delta jk equal to 1 if j equal k, 0 if j not equal k. And also another people might forgot is this computational basis or standard basis. It's this 0, 1 to n, and in terms of vector, it's this at I plus 1 entry, you have a 1, and all other places 0. So the 0 ket is 1, 0, 0, 0, 0. And 1 ket is 0, 1, and all are 0. And at the end, we have n minus 1 is all 0 and 1 at the end for n-dimensional space. Okay, so this is n dimension and log 2 of n, log sub 2 of n qubits. Okay, and yeah, so here, I guess most importantly, you need to remember the name computational basis. Okay, computational basis means this thing. Okay. And yeah, let's keep reviewing more gates in quantum circuit. So there is also CNOT gate and CZ gate. Okay. And they look like this thing and this thing. Okay. So when you draw on circuit, CNOT gate will look like this, and CZ gate will look like this. Okay. Yeah. And CNOT gate, if you write down in matrix notation, it's this block matrix of identity and X, and a 4x4 matrix like this. And so what you do is basically apply a control the X gate. So control on first qubit, depending on first qubit is 0 or 1, you will either apply X gate or not apply X gate on the second qubit. And the X gate is also just a NOT gate. So you think about what the X gate do, it basically just apply the NOT gate on this qubit. Okay. And yeah, so you will add 1 on this qubit, XOR 1 on this qubit when you apply so X gate. And anyway, so if you think about what the CNOT gate will do to a computational basis state AB, and the state will become A and A O plus B. And this O plus means XOR, so means addition of 2. And so there's a CNOT gate, which is a CS gate, and there's also CZ gate. Okay? And CZ gate is a symmetric between these two entries, because you see if you do CZ on AB, it's minus 1 to the A times B and AB, and so it's symmetric on both entries, so it's written like this. It's just two control dots here. Okay. And yeah, and in more general, we have this control unitary will be written as this. So you have this solid dot and control line and your unitary here. So this is a control unitary. And if it's A here, you have a U to A on the second qubit. And then there is also swap gate. It looks like this. It will swap those two qubits. Is a cross and line the cross. So if you are sci-fi, and I think you do this in homework or one of the homework with the answer given. So if you have sci-fi, you will swap those two qubits and become phi side. Okay. So there is swap gate, and then there is Toffoli gate. Is a control NOT. So you see that you have two control here and not here. And what this thing do is you apply a NOT gate on the third qubit, if only if the first two qubits are both 1. So you have this O plus A times B. So only when A and B both 1, you have a plus 1 here. And here we're also giving something that we forgot to talk about in class. That's control Z gate. And yeah, so it's like control Z gate, but it's not 3 qubit, and once again it's symmetric between all 3 qubits. So we just write we just draw it in this really symmetric form. So you have 3 control dots here, and it means control Z. Okay, so you have minus 1 to the ABC in front of basically everything, because it's just a scalar factor. And so you get this minus 1 to the ABC phase only when both ABC are 1. Okay, so get this, or I should say, get a minus 1 phase only when both ABC are 1. All of the 3 ABC are 1. Okay, And yeah, so let's say we have this circuit calculation tip. So to do this circuit calculation, usually you can do this computational basis calculation will make things a bit easier. As you start, you rather stay always in computational basis and they just think about what each gate will do to computational basis state. So the to the state will give you -1 to a the on A give you -1 to a AA, and X on A will be A plus 1, so you flip A 0 and 1 between 0 and 1 of this A, and the gamma 0 become plus state, which will actually give you more state. So become so you have one computational basis become two computational bases. So you have a 0 plus 1 up to some normalization, and the hands on 1 becomes 0 minus 1 with normalization. And also C naught AB is A and A plus B, and control Z AB is -1 to the AB, AB. So we have this calculation rule. You can usually do this to calculate the output of your circuit, output state of your circuit. And yeah, and you can also do the calculation by writing on the 2 dimensional vector, but will be more complicated to do. And yeah, some easy example. If you go through HEDMA and C naught, then your 0, 0 will become beta 0, 0. So this is how you transform between computational basis and Bell basis. And yeah, so up to here you have 1 square root 2 0 plus 1 and 0 here. Then C naught put this 0, 0, still 0, 0, and 1, 1 become 1, 0 become 1, 1. And yeah, we also have an example here. You have ABC here, you have C naught and C naught, and Z here. And here we have arbitrary computational basis state, and we'll ask you to calculate this for arbitrary computational basis state. And but you can still do this algebraically because you have all those rules that works algebraically. I guess when you have no HEDMA. Okay. And yeah, I guess we should write down what does the HEDMA do to algebraically, but I don't have. Okay, so I will try. Don't have a drawing tablet here, so HEDMA A will equal to 1 over square root 2. So if you try to write those two things in one equation, it's 1 over square root 2, 0. And then you have this plus minus here, depend on it's 0, 1, so it's so plus and minus 1 to the A. It's really hard. Plus and minus 1 to the A, and 1 here. Okay, so even with HEDMA, you can also do this, but you will have both 0 and 1 here. Yeah, hopefully it's readable. Okay, let me try to draw this a bit better. 0 and 0, yeah, like this. Okay, and anyway, but in this example we have no HEDMA, so it's quite easy. So ABC, and so C naught here, so you add the first register to second register, so B, A, and B plus A, or A plus B. And third register is still C, then you do C naught, and so you add this B plus A to a third register, so it's C plus A plus B, and finally you do Z on first register, so you have -1 to the A here. Okay. So it's just a calculation example. And yeah, another example we have something that we erase entanglement. So basically we reverse the C naught here. So we start with already beta 0, 0 here. So it's this 0, 0 plus 1, 1, and you go through C naught, and then 0, 0 component still stay 0, 0, and the 1, 1 component 1, 1 component become 1, 0 because you add this first 1 to second 1, and the 1 plus 1 becomes 0 in MA2. Okay, so you have the 0, 0 and the 1, 0, and there will be plus and the 0. So it's exactly this state here. So this plus and 0 plus is 1 over square root 2, 0 plus 1. Yeah. Okay, so yeah, it's this, and then we go a bit backward to derive notation review. So remember we have this bra and cat, or cat and bra. So cat vector is like the straight line and angle, and the bra vector is this angle and the straight line, and the cat vector is a column vector, and the bra vector is a row vector. But here, important thing is that we have this duality between bra and cat. So when we already run down a bra or already run down cat, we also define the corresponding cat and bra. So for example, you already have this cat vector here, then you already define this bra vector is a joint of it, or the Dagger operation, or transpose conjugate. So you need to transpose this vector and do conjugate. So you transpose this, it becomes 1 I in a row vector, and you do conjugate, so this I becomes minus I. Okay. So we have this adjoint operation. And yeah, and we have the inner product of two vectors is you adjoin the first vector, then multiply the second vector. Okay. So yeah, so AB times BW is A star B times this V bra times W V bra times W cat. And the most important thing here is, once again, inner product is a number. Okay. And also there is a complex conjugation with respect to the first vector here. You see you have A star here. So that when you have inner product of two complex vector, inner product with a complex vector with itself, it will become it's a non-square, which will be a positive number. For example, we have psi inner product with psi here, and there is also outer product, which is cat vector times a bra vector, and it will become a matrix. Okay. And yeah, I think this will actually be a PSD matrix, but that's something else to be proved. Okay. And in terms of tensor product, tensor product is a really interesting operation defined. Actually, any two matrix of any two sides, and we can have this product. This is different from usual matrix multiplication. It's like a multiplication, but it's a really huge multiplication. So you have n by n matrix and p by q matrix. A tensor B is m times p times n times q dimensional matrix. So it's a really huge matrix. And we define it with this entry-wise definition. So we have a whole bunch of B matrix in blocks, and so first block is multiplied with this coefficient A11, which is the 1 element of matrix A, and then you have A21 block, A31 block, all the way to AN1 block, and also all other blocks here. Okay, so this is a huge matrix with multiple blocks of B matrix multiplying with these coefficients of A matrix. Okay. And tensor product satisfies zero property. For example, you have the usual product property here. Okay. And the most important property that we use a lot is tensor product respect when you have tensor product of one thing time multiplying and do matrix multiplication with another tensor product, and then you are just doing multiplication with the slots. Okay. So tensor product give you two slots here, and further matrix multiplication will respect this slot. So A tensor B times C tensor D will equal to AC times BD. And of course, this is only satisfied when A times C and B times D defined. So you can only do this when the middle dimension between A and C match, and the middle dimension between B and D match. Okay, so this is the most important rule about tensor product. We like this slot notation, and we use tensor product to denote different quantum registers. And we already see the example. For example, all those quantum states, we have a tensor product between first qubit and the second qubit, etc. Okay. So we have tensor product, and we have this. We have a very general definition of tensor product here. So those matrix can be any dimension, so we can have a tensor product between operators, and we can also have a tensor product between kth vector or tensor product between broad vector, etc. As long as you are just operating it on something that fits this rule, you can have your tensor product works. Okay. And another very important rule about tensor product is when you do a joint, okay, and a joint of a tensor product is a tensor product of the joint. And the important thing here is the order doesn't change. So A tensor product with B, you think about it as a joint, is A a joint, tensor B a joint. Okay. And it's different from matrix multiplication. So matrix multiplication, when you do transpose a joint, then the order will change. So you have A times B a joint, it's B dagger times A dagger. But tensor product, the order doesn't change. It's important. And in particular, when you have two kth vector tensor together, and you do a joint, and they become two broad vector, and the order of broad vector is same as the order of the k vector. So v kt w, your joint it become broad v and broad w. Okay, so yeah, those are important thing about tensor product. And yeah, here we have some example of tensor product calculation. So we have this EPR pair 0, 0 plus 1, 1, and you have what happens when you project the first qubit to the plus state and do nothing on the second qubit, and yeah, you will project onto something. Okay. And interestingly, you see that you have an entangled state, but when you project the first qubit to a plus state, then the second qubit also become plus state, and they actually become a product state. Okay. So you have an entangled state, and they project the first qubit to some pure state, and the total state become a product state. Okay. And yeah, and here I guess we don't have too much time, so let's skip the detailed calculation. And then let's give and talk about something else, and about measurement. So yeah, so measurement is really confusing because there are different formulation of measurement, and once again, yeah, so this is I guess a really important slide, so please remember this. And it's very likely that you have an exam that you have an exam question that's like the homework question you already see, that asks you to do measurements in different formulations. Okay. And yeah, so we have 3+1 formulation. So in our circuit model, we say we assume our measurement in this most basic measurement model, that's a measurement in computational basis. Okay. But we also can have a slight generalization, saying we have a measurement in any orthogonal basis of your Hilbert space, and we can measure Hermitian operator, and we can do generalized measurement, which is characterized by this set of operator Mi. And yeah, so let's go through a definition of a different measurement. So you measure quantum state against the orthogonal basis. What happens is that one of the basis elements will get peaked, and your state will collapse into that basis element and basis state. And the probability of a particular I chosen is inner product square between Vi and USI. So basically the coefficient or coordinate, I guess coefficient of USI in this Vi basis on the ice coordinate. Okay, so Pi is this absolute non-square of Vi and the psi. Okay, so this is measurement against orthogonal basis. And we can also do measurement against any Hermitian operator. And for example, we can measure by sigma x, measure sigma x or sigma y or sigma z of a qubit. And Hermitian A. And we think about this by saying that A is Hermitian, so it's unitarily diagonalizable. So it can be written as this. So it's summation over some of the different eigenvalues and projector onto the corresponding eigenvalue. So eigenvalue lambda are real, and Vi are corresponding eigenvectors. Sorry, projected onto corresponding eigenvectors. Okay. So measure is A is basically measuring this orthonormal basis Vi, but there are two things, and the first thing is just syntactic. So the outcome now we don't say the outcome those arbitrary index I. The outcome are just the eigenvalue, and they correspond to some physical number. Okay. So the outcomes will be just the orthonormal I. And also the something might happen is there can be degeneracy. Okay. So those there are some maybe some lambda I will be for some different I lambda I will be the same. Okay. So actually instead of getting outcome as just orthonormal basis element, what we are doing is we'll project onto eigenspace that correspond to an eigenvalue. Okay. So say if you have several different lambda I that will equal to eigenvalue m, then you can define this projector Pm that's just a sum over all projector, sum over the projector that correspond to all the eigenvector of those same eigenvalue. Okay. And yeah, so you have a degeneracy. Instead of getting outcome as Vi, you get the outcome that's projected by this Pm. Okay. So yeah, we're going over a little bit. So however, degeneracy, we can write A as the sum over different eigenvalue m and those projector onto different eigenspaces. And yeah, and how you calculate the post-measurement state is and the probability is basically you want to calculate Pn of psi for different eigenvalue m. And so the probability of getting outcome I is this Pn of psi and absolute value squared, and which will also equal to Pn sandwiched by your psi. And yeah, and then the post-measurement state is this Pn psi and normalized. Okay. And yeah, and another important thing about Hermitian operator is you can calculate the expected value pretty fast. So you can calculate the average value or expected value of operator without even doing this eigenvector decomposition. You can just you have your vector. You can just sandwich your A with your eigenvector. So you have with your vector to be measured. So it's this psi bra A times psi k, and this is a nice trick that can be used in several places. It saves a lot of calculation because you can calculate this without doing the eigenvalue decomposition. Okay. And then we have finally we have this generalized measurement, and the generalized measurement is written as this operator m. Okay. And yeah, this is set of operator, and it can be just really any n by n matrix. Okay. And they don't even need to be Hermitian or anything. They just need to satisfy this completeness relation. The summation of m dagger m equal to identity. Okay. And yeah, and so there are different outcomes indexed by I, and the hint here is you want to calculate the probability and the post-measurement state. Basically, you calculate mi psi. So the post-measurement state is basically mi psi and divided by its norm. So it's normalized by dividing norm, becoming unique vector. And the outcome probability is mi psi absolute value squared. Okay. Like this. Okay, so we are showing time, and let's try to go little more, little fast, and I guess in the middle I should say also remember there is also this POVN thing, that is basically you do a generalized measurement, but you don't want to keep track of the post-measurement state, and then you can just keep track of those EI that's mi dagger mi. I think we are missing this. EI that's mi dagger mi, and you have summation I and EI equal to identity. Okay, so those are POVN, and you can use POVN to calculate the measurement probability. So measurement probability will be trace. I guess we should talk about, but it's okay because already no density operator. So the measurement probability will be trace EI rho. Okay. Rho is the density matrix. Okay. So I guess we jump ahead a little bit. So also we have a density matrix that's corresponding to an ensemble of quantum state. So we have an ensemble quantum state, we can write it corresponding density matrix. So those ensemble has probability pi of if zero probability pi and the pure state psi, and the density matrix will be sum over, so basically average over projector on two sides, so sum over I and pi psi. And so if the density matrix got acted on by unitary, you will evolve according to rho become U rho U dagger. And if you measure it with some measurement operator, with some measurement set of measurement operator n sub m, and the state will basically become n sub m rho n sub m dagger. So the probability will be this in trace, and the normalized state will be post-measurement state. When you get outcome small m, will be this thing normalized by its trace. This thing divided by its trace, because you want density matrix to always have a trace 1 and PSD. Okay. And but here we also have a different weird thing that you can also do measurement, but kind of not looking at the outcome. Then the post-measurement state will be low state distributed with this probability, and then you mixture them together, you see it's actually a simpler form, just the sum over m and rho and dagger. Okay. And let's give the calculation example because we are short on time. Okay, so we can have example measurement, and yeah, and density operator we can have. This very general definition is just any square matrix with trace 1 and being PSD. And we say that if you have those, you can always find some example corresponding to the density operator. Okay. And yeah, and here we have a way to test whether your state is a pure state or a mixed state. Pure state means that it corresponds to just one state. And if trace 0 square equal to 1, you correspond to a pure state. Trace 0 square is smaller than 1, it's a mixed state. Okay. And yeah, you can have different examples that give you the same density matrix. And in the more detailed slide, we have the exact equation, exact theorem tells you that when this happens. And yeah, and finally, in the next 10 minutes, we have a very important concepts correspond to composite system. This is a reduced density matrix. So we have been spending some time talking about density matrix, and the biggest application is this reduced density matrix. That says that you have a composite system, you can calculate a density matrix that tells you everything about a small subsystem. So you start from some rho A, then you can calculate this trace B rho A B to get a reduced density matrix rho A. Okay. And trace B is this partial trace operation. It's defined by those two things. So if you have a tensor of one thing and another thing, then you just trace the second thing, become a matrix on the first register. Okay, and then you extend to everything by linearity. Okay. And you have some properties. So the trace B, you can also do this summation over sandwiching with summation over sandwiching with this basis of basis vector of B. And also if you trace A, then trace B become a number. This should usually become 1 if your rho is normalized. Then you can trace A and the trace B will trace out everything, and the trace B and the trace A will trace out everything. And yeah, will be equal to trace over this matrix. Okay, the yeah. Here, I guess I didn't say this very clear, but these two property, the row AB don't need to be a density matrix. This works for any matrix row AB. Okay. And we have Schmidt decomposition. That's kind of going to the reverse of partial trace. And so this is a theorem about entanglement. We say we have a pure state that on two systems. Then you can always return this Schmidt decomposition form. So sum over I, lambda I, and IA, IB. So IA is the set of I is orthonormal basis for A, and set of IB is another orthonormal basis for B. And the important thing here is the summation. This I index is the same for all those three things. You have lambda I and IA and IB. And the lambda I are the streaming coefficients. They are non-negative real numbers. Okay, we have summation lambda I squared equal to 1. Okay, yeah, yeah, and yeah, from here you can see that row A will equal to row A and row B will have the same eigenvalues, all those lambda I squares. Yeah. And then finally we can talk about the reverse of partial trace. That's this purification. So this operation that says that whenever we have a density matrix row A, we can find another system R such that and pure state AR such that if you do partial trace on R, then this AR become your density matrix row A. Okay. And yeah, there's a theorem says that every density matrix row can be purified. Okay. And I guess I should put the total conclusion slide here, but it's not here. And I guess finally, let's jump to the part of classical computation that's most important to us. That's this symplectic notation, and we have several of those big O notation. Okay. And so this f of n equal to O G of n means that basically means that f of n is less than or equal to G of n when n goes to infinity. And in terms of yeah, and we have the exact definition here. So f of n less equal to some constant G of n when n is greater than some n zero. So, and then we also have this omega notation. So that we write f of n equal to omega G of n. That basically means f of n is greater or equal to some constant times G of n when n is large enough. And then we have a big theta notation, means that f of n is within some constant factor between over just equal to G of n when n go to infinity. And then we have those two less used notation, small and small omega. The f of n equal to small of n means that f of n is less than G of n when n goes to infinity. Okay. And different part, very different part is that this needs to be for constant c. So no matter how small the c is, f of n needs to be smaller than G of n. And then also the corresponding small omega notation means f of n is greater than c G of n for any constant c. And here we have the cheat sheet for some going rate of some functions. So the constant will, when n go to infinity, will be less than log n, and log n will be less equal to poly log n, depending on how big your poly is. I guess here is you have a frictional poly will be actually slower, but so I guess here it should be a bit of a question mark. It will be about equal. Okay, so between n and the poly n is like I think here it should be like a parenthesis. So let me like this, okay? Because when we say poly, we usually poly any number, okay? Okay. So yeah, so log_n or polylog_n, okay. And anyway, but the polylog_n will be always less than n when n go to infinity, and then you can also say just poly_n here, and and any poly_n for any poly will be less or equal to 2 to the n, and 2 to the n will be less than n factorial when n go to infinity. Okay. And yeah, I think that's all I want to review here, and I will try to put the, yeah, I will put we have a nice we have a nice conclusion slide between purification and reducency matrix before on our slide. I'll put it here and re-upload this review sheet. Okay. And I guess we can stop 2 minutes or 1 minute earlier. And yeah, good luck on your midterm on Thursday. Okay, that's it.